Past paper time. I've got Edexcel A-Level Maths 2019 paper 1. So this is pure maths, right? I've not actually seen this paper before. And that is because I wanted to make this video natural, right? You're going to see me seeing these questions for the first time. You're going to see the thought process as I go through. And hopefully that's going to be more valuable than me just reeling off a load of solutions, because, you know, you're going to be in the exam yourself and you're going to have to look at questions that are definitely difficult and you're going to have to think about them, right? So let's just jump straight in. I've got my calculator, got my lockdown haircut. Let's have a look at question 1. So we've got some cubic expression here, and it says that given that x plus 3 is a factor of this expression, find the value of the constant a. Right, so classic factor theorem. So if x plus 3 is a factor of f of x, that means that f of minus 3 is going to equal 0. So it is just a case of subbing x for minus 3 in and just, you know, playing about with it a bit, right? So we're going to get 3 times by minus 3 cubed plus 2a times by minus 3 squared minus 4 times minus 3 plus 5a, and then that's going to be equal to 0. Be really careful, make sure you put all your brackets in here, super important. Okay, so what is minus 3 cubed? It's going to be minus 27, plus 2a times minus 3 squared, which is 9. Minus 4 times minus 3 is going to be plus 12, plus 5a equals 0. Let's do a tiny bit more simplification on these two terms here. 3 times 27 is going to be 81, so I'm going to get minus 81, and then plus 18a, plus 12, plus 5a equals 0, right? So we've got a couple of a terms and a couple of number terms. Get them all together, solve for a, Bob's your uncle. Minus 81 plus 12 is going to be minus 69. Plus 18a plus 5a is going to be plus 23a. That's all going to equal 0, so we're going to get 23a equals 69, which implies that a equals 69 over 23, which equals 3. Sweet. Few marks to get things going. Cool. Question 2. Figure 1 shows a plot of the part of the curve with equation y equals cos x, where x is measured in radians. Diagram 1, on the opposite page, it's got to be figure 1. Cool. Use diagram 1 to show why the equation cos x minus 2x minus a half equals 0 has only one real. Okay, so using diagrams to show how many solutions of an equation has is usually to do with drawing two curves or two lines, whatever, and seeing how many times they intersect. Because to get the intersections of two graphs, we usually solve equations simultaneously. So if this equation here is to do with kind of me trying to solve two simultaneous equations that are represented by graphs on this diagram, and they only intersect once, then that equation is only going to have one root. So I'll show you what I'm on about here. We know we have the graph of y equals cos x already here. So then the question is, how do we go from cos x minus 2x minus a half equals 0 to two separate lines represented by y equals? Well, I'm going to need this cos x on my own. So if I add 2x and add a half to both sides, I'm going to get cos x equals 2x plus a half. If I now take the curve y equals, well, a line, y equals 2x plus a half, sketch it, you can see here that if I was to try and solve these two equations simultaneously, I would get this equation, wouldn't I? I'd put the y's equal to each other and I would get this equation. What I'm going to do is I'm going to put this on the diagram and hopefully they only hit each other once. So they're quite nice here because this is pretty much to scale, isn't it? One of these squares is going to represent 1. You can see that cos is measured in radians, and cos hits at pi by 2, which is a bit more than 1.5, which we can see is about 1.5 squares in here. So we can relatively go to scale here. Y equals mx plus c. C is going to be a half, and the gradient is going to be 2. So if I go 1 across here, I'm going to go 2 up here. Just sketch the line, right? Not going to look beautiful, but we're not doing art. Straight away there, and we know that this is the line y equals 2x half. We can clearly see that they intersect. So it's easy as that. I'm just going to say, lines intersect once, therefore only one solution. Fantastic. Part B. Given that the root of the equation is alpha and that alpha is small, use the small angle approximation for cos x to estimate the value of alpha to 3 decimal places. Okay, so what is the small angle approximation for cos? So it says that when theta is small and measured in radians, which is good because we know that in this case we're using radians, cos theta is approximately equal to 1 minus theta squared over 2. So just sub it in, right? Sub it in. So I'm now going to have 1 minus x squared over 2 minus 2x minus a half equals 0. Clean it up a bit. I'm going to times by 2 because I don't like fractions. So I'm going to get 2 minus x squared minus 4x minus 1 equals 0. Get this x squared positive because we're used to that, aren't we? So I'm going to add it to the other side, add the 4x to the other side, and then on the left I've got 2 minus 1, which is 1, and then I'm going to take that to the other side, so I'm going to get minus 1. Okay, I know I'm not going to be able to factorize this, and that is because the question says to estimate the value of alpha to 3 decimal places. So I'm not going to get some nice factorization here. It's going to be, you know, some irrational or number or some big decimal or something like that. So a few things I could do. I could use the quadratic formula. I could complete the square. Or I could be lazy, grab the calculator, go to the equation mode, select polynomial, select degree 2 because it's a quadratic, and then just stick the numbers in. So my x squared coefficient is 1. My x coefficient is 4. And the number on the end is minus 1. Stick it in an equals, and we're going to get our solution. So the first one, it says it's minus 2 plus root 5, which is going to be a positive number. So that is going to be 0.236 to 3 decimal places. And then press equals again, we're going to get the other one, but we are going to see that this thing here is negative, and we can see from the diagram that alpha is positive. So this is the value that we care about. And we are good. Right, looks like we have some differentiation. We're getting into it. So show that dy by dx equals a over x plus 1 to the n, where a and n are constants to be found. Okay, so what's y? Y is a fraction. And how do we differentiate fractions? We use the quotient. So the way I remember it is as follows. We're going to have dy by dx equals, and then we're going to write down the bottom. So that's going to be x plus 1 squared times by the derivative of the top. So that's going to be 10x plus 10. Minus, and then the other way around. So we are going to write down the top, so that's going to be 5x squared plus 10x times by the derivative of the bottom. So the derivative of the bottom, we're going to use the chain rule, and it's going to be 2 times x plus 1. Easy as, right? All of that is going to be over the bottom squared. So that's going to be x plus 1. Right. So be careful here. Please don't jump in to just multiplying everything out because it's going to get messy, right? See if you can do anything cheeky. See if you can factorize anything, and then you might be able to cancel stuff down before you go on multiplying 3 brackets together. For example, I can see that this top bit here, 10x plus 10, I can factorize that. I can take a 10 out, and then look what's going to be inside. I'm going to get 10 times x plus 1. So then if I've got an x plus 1 here, multiplied by x plus 1 squared, that's going to be x plus 1 cubed. Can you see how this is getting a bit nice before I then go crazy? There's going to be a bit of work to do, but I'm making it less, trust me. So, similar thing here. Looks like I can take a 5x out of this here. So this is going to be 5x, and then what am I going to be left with? I'm going to be left with x plus 2. Cool. And then that's still times by 2, x plus 1. And then obviously the x plus 1, the 4 on the bottom. Okay, what can we do now? Looks like I can cancel an x plus 1, right? Because there is 1 in every term. I'm going to do that. I'm going to get 10 times x plus 1 squared. And then what am I going to be left with here? This is gone. And then let's just times this 2 by this 5x quickly. So I'm going to get 10x times by x plus 2. Okay, so it's cleaning up. It's cleaning up. All of that is now over. Well, how many x plus 1s have I got left? I've got 3 of them. Right, I think at this point, I'm going to have to multiply out because there's no way else to do it. So I'm going to get 10 times by x squared plus 2x plus 1, and then minus 10x times by x is 10x squared, and then minus 10x times by 2, which is 20. And then obviously all over the bottom. Right, let's clean up. So what do I have here? I'm going to have 20x squared. I'm not going to have 20x squared. I'm going to have 10x squared. See, this is This is what happens in exams. And then plus 20x plus 10. And then this is nice, right? Minus my 10x squared minus my 20x. And it's all going to work out nicely. Who would have thought? So what happens? 10x squared's gone. 20x gone. So what am I left with? 10 over x plus 1 cubed. What a life. Right. Deduce the range of values for which dy by dx is less than 0. Right, so the only variable thing is the bottom here, because the top's just 10 and it's always positive. So the only way that this whole thing is going to be negative is if the bottom is negative. So cubes can be negative, and the thing inside it has to be negative. So we need the thing inside this to be negative, i.e. we need x to be less than. And you can see here that it's actually, like, if x was equal to -1, dy by dx and y would just go a bit mad, but they've actually told us that x is not equal to -1 here, so it all kind of works out. Sweet! Question 4. Looks like we've got some binomial on our hands. Okay, so find the first 3 terms in ascending powers of x of the binomial expansion of 1 over the square root of 4 minus x. Okay, so the first thing we're always going to want to do is get it in the actual form that we can use the binomial in. So if you were to recall, the binomial expansion of 1 plus ax to the n, in your formula booklet, so don't you worry, is going to be 1 plus nax plus n times n minus 1 over 2 a squared x squared, and then I only care about these 3 terms, so I'm going to be lazy and not write anymore. Cool, so we're not quite in that form yet, are we? Because we have 1 over the square root of 4 minus x. So how do we get it in that form? Indices. So this is going to be the same as 4 minus x, then minus a half. Are we in the form yet? No, because, super careful, this has to be a 1. So how do we make that a 1? What we can do is we can take this 4 out, but do not just write this. It would be incorrect to do this. And the reason is because that 4 is still inside this bracket, which is to the power of minus a half. So this is also to the power of minus a half. So now we're good. We've just got a constant outside of it, which we'll multiply through later. But right now, we can just focus on the binomial expansion of 1 minus x over 4 to the minus a half. We're just going to directly apply this formula now. Not too bad. So 1 plus n, what's n? Minus a half. That's going to be minus a half times a, which is the coefficient of the x, which is minus a quarter. Minus a quarter times by x, and then one more term we get n, so minus a half times by n minus 1, which is going to be minus 3 over 2, all over 2 times by a squared, which is minus a quarter, all squared, times x squared. Okay, what do we get? 1 minus a half times minus a quarter is going to be plus an eighth, x. Right, now this term, just get your calculator out, don't be a hero, right? So I'm going to do minus a half times by minus 3 over 2, all over 2, times by a quarter squared. And then that is going to get me plus 3 over 128. So we're going to get that of an x squared. Is this our final answer? Not quite, because we still need to times by this 4 to the minus a half. So what is 4 to the minus a half? Well, it's going to be a half, right? So my expansion is going to be the following. A half times by all of this stuff. So then you just, halve each term, right? So that leads us to 1/2 plus 1/16 x plus 3 over 256 x squared. Just give it a little dot to really show that that's not exactly equal to that. Perfect. Okay, so now it's probably going to be about like subbing numbers in, getting estimations, talking about validity, etc. So let's have a quick look at this. Without evaluating your expansion, state, giving a reason, which of these 3 values of x should not be used. Okay, so there is the thing that we always need to remember, and that is the following. If I expand 1 plus ax to the n, we require that this must be less than 1. So the modulus of this must be less than 1 even. So we require this. So what that means is, in my case, I have the minus x over 4 I require this to be less than 1. Okay, so I've got a modulus here, so I can just forget about that minus. So this is going to be the same as x over 4, less than 1. I times through by 4, what do I get? I need to get that the modulus of x is less than 4 here. Well, look at this. The first thing that they give is an x equals minus 14. So does that satisfy the modulus of x being less than 4? No, it doesn't. So we would literally just say the modulus of minus 14 is greater than 4. Therefore, you know, x equals minus 14 is invalid. Boom. Easy as. Right, last bit now. State given a reason which of these three values of x would lead to the most accurate approximation to root 2. So that might not be as obvious. Basically, you want x to be as close to 0 as possible. Kind of as the modulus of it to be as small as possible. You get further away from 0, because obviously binomials are approximations, right? You get further away from 0, you start diverging a little more. So if you ever kind of asked about, you know, what's the most accurate, given that they're all valid, the one closest to 0. So you would literally say that. You would say x equals minus a half. And then you would just say, as it is the value closest to. Easy as that. Cool. Question 5. Looks like we're jumping into the quadratics. Okay, so the first bit looks like we're completing this square here. Really important, if there's a number in front of the x squared when you're completing the square, before you do any completing the square, remove it. So factorize it out and put it in a big kind of square bracket. And I want to do it square to really emphasize the fact that this is not the same as the bracket that is going to arise from completing the square. So what I mean by that is this. I'm going to take this 2 out of the first two terms. So it's just 2 times x squared plus 2x. And then I'm going to leave that 9 on the end. Because now what I've done is I've completely separated that 2 from any kind of completing the square efforts. So now what I'm going to do is just inside that bracket, complete the square and just forget about everything that's going on outside. So this is going to be 2, and then keep the brackets as usual and just work inside them. So complete the square as normal. That's going to be x plus 1 squared, and then I'll take away that 1 squared, so take away 1, and then leave everything else there. And now I can multiply it all out, because I've done the harder bit, right? So now this is going to be 2 times x plus 1 squared minus 2 plus 9, which is going to equal 2 times x plus 1 squared plus 7. Cool. So that is now going to make sketching this thing very easy because we have the minimum point. So it's really easy to sketch a quadratic when you have the minimum point because you just say, where's the minimum point? It's going to be at the negative of what number is here. So that's going to be minus 1. And then the y value is just going to be 7. So it's going to be minus 1, 7. We can say that's around here. And then we just draw a smiley face on top of it, just like that. So we can see instantly, without even doing any discriminant work or anything, that this thing is not going to hit the x-axis. And the only intersection is going to be this one here at the y-axis. So we get that from setting x equals 0. If you just look at the initial equation that's given, you can quite clearly see that the first two terms will go to 0, and we'll just get y equals 9. That's parts A and B done. Relatively easy. 6 marks, so we're having a good time. We're having a good time. Describe fully the transformation that maps the curve with the equation y equals f of x onto the equation with the curve y equals g of x. Okay, I like that. That's interesting. So we can clearly see that g of x is similar to f of x, right? The first thing that I'm noticing is this, instead of having 2x squared, we have 2 of x minus 2 squared. So the first thing that I would probably do right now is see how similar these things are. What do you think I could put into f of x that could start looking like g of x? If I did f of x minus 2, then instead of having an x there, I'm going to have the x minus 2 there. So I think this is going to go quite well. It might be g of x, it might not exactly be g of x, we'll see. So f of x minus 2 is going to be 2 times x minus 2 squared. Sweet, so that's looking like g of x. Then it's going to be plus 4 times x minus 2, and then plus 9. So this is the bit where it's starting to maybe diverge slightly from g of x, but let's multiply this out and kind of see where we are. So we've got 2 times x minus 2 squared. Cool, happy with that. Plus 4x minus 8 plus 9. Right, let's simplify and then kind of collect our thoughts. So this is going to be plus 1. It's not yet g of x, is it? Well, that's not the worst thing in the world, because we're allowed to change this and add things, take away things, right? So what if I was to just say, well, let's take f of x minus 2. And then what do I need to do to this thing here to get g of x? Well, the only difference is g of x has this minus 3 and I have a plus 1. So why don't I just take 4 from this? I take 4 from that, what am I going to get? I'm going to get 2 times x minus 2 squared plus 4x minus 3. And I go, wait a minute, that's just g of x. Now, why is any of this useful? Because from this function notation, we can directly read off translations. So, well, all transformations really, it just so happens to be a translation in this case. So what it is now is this f of x minus 2 represents a shift by 2 in the x. So that would be like if we kind of have a vector, that would correspond to going 2 positive in the x direction. X is always the one where it's kind of like the opposite to what you think. So you have a minus 2 here, it means it's plus 2 here. And then outside the bracket, we have this, which corresponds to the y direction, and that's going down by 4. So my answer would literally just be here. Now make sure you get the words. You always need the words here. So this would be a translation. And then you could say translation by or of, something like that. Translation by, and then you give the vector. So you've given the word, the kind of keyword of the transformation, and you've then described it. So that's going to be probably like your 2 marks here. Right, last part. Now find the range, so you know the different values that this thing can be. The function h of x equals 21 over 2x squared. Okay, right. So we can instantly recognize that this thing on the bottom of h of x is the function from part A, right? It's f of x. So what could we do that would help us with this question that we've already done, right? What could we apply that we've already done? Well, we've written f of x in this really nice complete in the square form, haven't we? And that's really useful because it tells us, you know, the minimum or the maximum, and that kind of gives us an idea of the values this thing can be. So if I, instead of writing h of x equals what they've given, write it as follows. So this is going to be what? My 2 times x minus 1. I believe that was an x plus 1 actually. X plus 1 squared plus 7. Then I can see here that the minimum value of the bottom, so I'll write this here, I'll write min val of the bottom, why not? The minimum value of the bottom is 7, okay? So as the bottom increases, the whole h of x actually decreases because we're dividing by a bigger number, aren't we? So the biggest value that this thing can be corresponds to the lowest value of the bottom. So I know that the maximum value of h of x is basically going to be 21 over 7. And 21 over 7, that's 3, right? So I know that h of x, it has to be smaller than 3. And it can be equal to 3, can't it? Because when the bottom is 7, this thing is equal to 3. And then, let's think. The bottom's just going to get bigger and bigger, go up to infinity. So if I have kind of 21 divided by infinity, it's basically going to go to 0. It's never going to get negative because there's nothing that's ever negative here, but it's going to go towards 0. It's never going to equal 0 though. So this isn't a greater than or equal to, it's just going to be a greater than. You know, it's going to be an asymptote. It's going to go towards 0, but never exactly equal. And that's question 5. Question 6. Oh, it's going to start getting dirty now, you know, when the trig comes out. Okay, so solve for theta between minus 180 and 180, the equation 5 sine 2 theta, oh, it's going to start kicking off now, and it equals 9 tan theta. Okay, so you're going to want to get it in terms of kind of one trig function or something like that. The first thing I'm noting is I've got a 2 theta here, but a theta here. That's not good. So I'm going to want to break this down into just thetas. So we know the double angle for sine is 2 sine theta cos theta. And now I've got sines and coses, so I'm feeling like it's going to be a good idea to swap that tan into a sine over cos. So let's do that as well. So that's going to be sine. Oh, here's an interesting one. Okay. Let's say I was to just do the following. Tell you what, so, you know, get this out. So I'm going to get 10 sine theta cos theta equals 9 sine theta over cos theta. And then let's say I just go, all right, sweet. Well, there's a sine on both sides. So I'm going to cancel them. So I'm going to get 10 cos theta equals 9 over cos theta. Oh, sweet. Times it through by cos theta, right? So I'm going to get 10 cos squared theta equals 9, which implies that cos squared theta equals 9 over 10, which implies that cos theta equals plus minus the square root of 9 over 10. Are we good? No, we are not. What have I done? You need to be so careful here. What is the step here that is not good? Which one is it? It is this. It is dividing by sine theta. You need to be so careful when you're dividing something that is variable, right? So that it's not just a number, it's not just a 6. When you're dividing something that, has x's in it or sine or anything, you need to make sure that this thing can't be equal to 0. Because what would happen if sine theta was equal to 0 here? Well, first of all, dividing by 0, not quite great. But also, we would be losing a solution, because if sine theta was equal to 0, this equation would be satisfied, wouldn't it? Because I get 0 equals 0. So if I just divide by sine theta, not accounting for the fact that it could be 0, I'm losing solutions there, aren't I? So here's what I would do. I would say, therefore, 10 cos theta equals 9 over cos theta, or sine theta equals 0. So now I've got my two kind of lines of equations that are both going to give me solutions. So you really need to pay attention to that. They like asking questions like that all the time, where it's like, spot Sally's mistake, and then it'll be something like this, right? So make sure you always think of that, especially in trig. They like it in trig. Now it's just a case of getting the values, right? Sine theta equals 0, that just hits at every 180 degrees on, both ways. So this straight away is going to lead me to theta equals minus 180, 0, and 180. If you don't believe me, draw the sine graph and look for yourself, because that is something that you should know how to draw. And then cos theta equals plus minus the square root of 9 over 10. So I've got two separate kind of ones that I'm solving here, aren't I? If you think of the cos graph, it's going to look something like... Oh, that looks awful. So, well, that's 360. I mean, this is 180, so we only really care about between these two lines here. Just here. So I want to solve plus, the square root of 9 over 10. So that's going to be, something around here. And then minus the square root of 9 over 10, so something around here. So you can see that I know I should have 1, 2, 3, 4 solutions in for these. So the first one I'm going to do, I'm going to get my calculator, I'm going to make sure it's in degrees, super important there, and I'm just going to get the inverse cos of the square root of 9 over 10. Right, so that is going to get me 18.4, basically. So that is going to correspond to this one here. So this is going to be 18.4. So then I ask myself, well, what are the other ones? So for cos, because this is an even function, that means this thing here is just going to be minus 18.4. So I'm going to get, essentially, I'm going to get plus minus 18.4 for there. And then the next one, if I do the inverse cos of negative all of that stuff, I'm going to get 161, and then rounding that, I'm going to get 0.6. So that's going to be corresponding to that one there, it's greater than 90. And again, because of cos being even, this one here is also going to be negative that. So I'm going to get a plus minus. So all of my solutions here, I get 1, 2, 3, 4, 5, 7 solutions. So it's a bit of a big one, but you get 6 marks. Right, part B, let's have a look. Deduce the smallest positive solution to the equation. Okay. So you can see here that we've just swapped, the only thing that's really changing is the angles inside these trig functions are changing. So definitely going to be able to use part A here. If you look, if you just basically set theta equal to x minus 25, that equation is going to turn up, isn't it? Because the 2 theta is then going to be 2x minus 50. So essentially, all of my solutions for x minus 25 are going to be these ones here, the ones for theta. So, I'm going to get the plus minus 18.4. I'm going to get the 0. I'm going to get all of them, basically. And I'm interested in the smallest positive solution. So we need to be super careful here, because the smallest positive solution, for theta, obviously we've got like the 0, but then we've got the 18.4, stuff like that. But that wouldn't be the smallest positive solution for x, would it? because we're going to then add a 25. So if you think about it, if we choose the minus 18.4, which is obviously negative for theta, but then we add the 25 to it, we're going to get 25 minus 18.4, which is going to be positive, and that is going to be our smallest one. So if I just do 25 minus 18.4, I am going to get 6.6. So that's, yeah, little one to look out for there. Okay, we've got through the first trig question. This is good. Right then, question 7. Oh, it's getting bigger, innit? They're getting bigger. Oh, okay, you hit that halfway point. Okay, let's have a look. In a simple model, the value V of a car depends on its age t in years. Makes sense. The following information is available for car A. Its value when it's new is 20 grand, its value after 1 year is 16 grand. Okay, going to be setting up some equations here. Use an exponential model to form for car A a possible equation linking V with t. So that's not an easy question. I can see students kind of not really knowing what to do there. Usually they would give you the form of the model, and then you could then do the equations, but they're asking you to actually know what it should look like. Not an easy question. So there's a couple of things that you could do. So generally, an exponential model, a lot of the time you could have an e in it, so you could have like e and then to the power of kt, k or whatever other constant you choose, is generally k. So some constant times by t. The reason you need this constant here is because e to the t is always then just going to kind of increase in one set way. But, you know, that can't represent everything. Things increase a different way, right? So we're going to need that k in there to kind of encapsulate that. And then we're going to need a constant at the front that would represent its initial value. So essentially, when t equals 0, this thing is going to be 1. So then we're going to need something at the front that says, right, my initial value of this thing, so we can call that a for example. It wouldn't be wrong to do a different number to the power of t as well, because if you think about it, e to the k, you know, once you work out k, is going to be some other number, some constant. So then that could also be the same as like b to the power of t. So there's a couple of things you can do here, and that's why it's quite difficult that they didn't give you the model here. I'd stick to the e's, generally a good bet. Okay, so now it's actually just kind of using the information given to get these values of a and k. So its value when it's new, well, we just talked about that, the initial value. So a is going to be 20,000. And just to prove that to you, v when t equals 0, so v is a function of t, when t equals 0 is going to equal a times e to the 0, which is going to equal a, which we're told that initial value is 20. Okay, its value after 1 year is 16,000, so v when t equals 1 is going to equal 20,000 times by e to the k and then times 1. And we're told that that is going to be equal to 16. Now it's just equation time, right? Divide by the 20,000, we're going to get e to the k equals 16 over 20. So straight away now, how do we solve these equations? We use the natural logarithm. So that is going to tell us that k is going to be equal to the ln of 16 over 20. I know you can simplify 16 over 20, but it's going straight into my calculator, so I don't really care. And that's going to get me to a few decimal places, minus 0.223. Now this makes sense. And the reason is, the value of this car is going to be going down, right? Cars don't go up in value, generally, most of the time, you know, as time goes on. So the fact that we have this negative value of k means that this exponential curve is actually going to be a negative exponential curve. So the value is going down over time. So my, you know, final model will be v as a function of time is going to be 20,000 times by e to the minus 0.223 t. Cool. Nice. That was actually the chunk of the question, it looks like. So let's have a look now. The value of car A is monitored over a 10-year period. Value after 10 years is 2 grand. Evaluate the reliability of your model in light of this information. So what we would have to do is just say, well, what does our model predict for the value of the car A after 10 years? So it's as simple as sub in t equals 10. So we're going to get 20,000 times by e to the minus 0.223 times by 10. Straight to your calculator, 20,000 multiplied by, where's my e button? Here it is, e to the power of minus 0.223 times 10. And I get, well, to the nearest pound, 2,100 and 2,150, 2,150 0.56, about that. So I'll just put 1 here. It's obviously not 2000, but it's not too far off, is it? So I'd probably say that, you know, that's more or less 2000. So, you know, my model's not going to be perfect. I would say, you know, therefore, it's pretty reliable. I think in these questions, though, you know, as long as you do the maths right and then you give some kind of reasonable argument to your examiner, you're probably going to be fine here. But I'd say it's relatively reliable. Okay, so the following information is available for another car. It has the same value when the car is new. Okay, so 20 grand when it starts. That constant A is going to be that 20 grand. Value depreciates more slowly than that of car A. Okay, cool. So our model is kind of the form V equals initial price times e to the kt. The only thing that this really dictates is that initial price. And then the whole movement, you know, the kind of changes in the value of the car is really to do with this. And what is the thing that actually determines how quickly it goes up or down? It's this K, isn't it? Remember when I said that the fact that K was negative means that it goes down? Well, imagine if K was more negative, it would go down quickly. If it was less negative, it would go down, still go down, but a bit more slowly. So this says its value depreciates more slowly. So that would mean that K would essentially be kind of less negative, right? So it would be a smaller kind of absolute value of K. And the value of A, because it has the same initial value, A would be the same. It would be the same. And I reckon that's enough for my mark. Sweet. Question 8. Figure 2 shows a sketch of a part of a curve with equation y equals x, x plus 2x minus 4. Okay, this is nice. So this is a cubic equation, but they've given it us in pre-factorized form. So what that tells me is I'm going to be able to get the x coordinates of where it hits the x-axis very easily. The region R, shown shaded in figure 2, is bounded by the curve in the negative x-axis. Show that the exact area of R is 20 over 3. All right. Integration. I was wondering when he was going to show his face. Part A is pretty standard integral, right? It's this area R1, which is on the negative x side. So what we're going to do is we're going to need to get the point where it hits the x-axis, where the x-coordinate is negative, and then just integrate there and 0. So first thing I'm going to do is, where is it going to hit the x-axis? Looking at this, it's the places that makes y equals 0. So we know that it's going to hit at x equals 0, x equals minus 2, and x equals 4. That's super important. Now I've got the information from the factorized stuff, I'm actually going to multiply this out because it's going to be a lot easier for me to integrate it that way. So let's multiply out these two brackets first. So I'm going to get x squared, and then I'm going to get minus 4x plus 2x minus 8. So these two are just going to turn into a minus 2x, and then I'm going to multiply it all by x. So I'm going to get x cubed, and then that minus 2x is going to turn into a minus 2x squared. And then minus 8 is just going to turn into a minus 8x. So that tells me that my region R1 is going to be the integral between 0, which is the top limit, right, the origin, and then minus 2, because that's where it hits the x-axis. And then all of this curve here. So x cubed minus 2x squared minus 8x. So we should hopefully know what to do here. Just straight up integrate it, right? So it's a definite integral, so I'm going to put my square brackets ready, and then I'm just going to integrate. So I'm going to get a quarter x to the 4. Remember, add 1 to the power divided by the new power. Minus 2 over 3x cubed minus 4x squared, and then I don't need a c because I'm doing a definite integral. So limits here, 0, minus 2. This is quite nice. The 0, all of these terms just have, you know, powers of x in them. They're all going to go to 0. So this first bracket, that would be the kind of 0 bracket, it's just 0. That makes my life just that bit easier. Second one, probably not as easy, but let's just jump in. So I'm going to get 1 quarter times by minus 2 to the 4 minus 2/3, definitely didn't give myself enough space in this bracket, times by minus 2 cubed minus 4 times minus 2 squared, and then get it all into your calculator. Don't do it in your head, don't be a hero. Right, so I'm going to get a quarter, I'm going to work out this bracket, and then I'll just kind of do the negative of it. So times minus 2 to the power of 4 minus 2 over 3 times by minus 2 cubed minus 4 times by minus 2 squared, and that is going to get me minus 20 over 3. Perfect. So then obviously that's minus 20 over 3, which is 20 over 3. Fantastic. Okay, so that is our 1. Let's have a look at part B. The region R2, also shown shaded in figure 2, right, is bounded by the curve, the positive x-axis, and the line with equation x equals b. B is a positive constant, and b is between 0 and 4. Given that the area of R1 is equal to the area of R2, verify that b satisfies the equation. Ooh. That's not nice. That is disgusting. That is disgusting. Right, okay, so don't let this equation scare you. It's probably not that obvious where this equation is coming from right now. So I can see a lot of people in the exam going, just looking at that final result and saying, I am nowhere near that. What is going on? Don't even worry about it for now, right? Don't worry about it for now. Essentially, you know, the question is always going to follow this format. You're given a piece of information, you're going to get an equation from it. So and then you do all the stuff at the end, but let's just worry about that bit first. Because maybe we can at least get started, and then this equation is kind of going to start to, like, you know, pop in at some point. So let's have a look at this. What piece of information are we given, and how can we get an equation from that? The area of R1, which we know, right, it's 20 over 3, is equal to, so you see, I'm just translating this English into maths, right? The area of R1, 20 over 3, is equal to the area of R2. Okay, right, so now imagine it just says find the area of R2. What would you do to work that out? Well, you can see that it's an integral, right? You know the limits are going to be 0 and b, and it's the integral of the curve, right? So what's that telling me? That is telling me that the integral between 0 and b of my curve, which we found to be x cubed minus 2x squared minus 8x, is going to be equal to the area of R1. Now, I've made a mistake here, and that is the fact that it won't actually be equal to 20 over 3. And that's because the area of R2 is underneath the x-axis. So when I get the area of something, when I get the integral of something, and the area is underneath the x-axis, it's actually going to give me a negative number. And then the true area is just going to be the kind of positive version of that. So that means if I was to do this integral, I would actually get minus 20 over 3. And then I would conclude, okay, that means that the area, you know, the magnitude of it is 20 over 3. So this might look pretty horrendous, but I've actually got some, you know, I've got an equation here. So, I mean, I've already integrated this, actually. But I mean, I'll just do it again for you. What was it? It was a quarter x to the 4 minus 2/3 x cubed minus 4x squared, right? And that's between b and 0. Okay, so this is cool, because the 0 now, that's just going to get, I'm going to get some b bracket, and then minus a 0, because again, sub x equals 0 into here, it all goes to nothing. So I'm going to get a quarter b to the 4 minus 2/3 b cubed minus 4b squared. I'm getting a bit of an equation, right? Let's just sort all of this out. I'm going to try and get rid of these fractions here. So you can see that I've got 3s and 4s. If I want to get rid of everything, if I times up by 12, that should sort me out. So this would get me minus 80, because the 3 cancels, and then I've got to times it by 4 still. So I get minus 80 equals, times this by 12, so it's going to be 3b to the 4. This is going to be 8b cubed. And 4 times 12 is 48, so that's going to be minus 48b squared. Okay, so we're getting an equation at least. Let's get this all onto one side. So what I'm going to do is I'm going to make sure this is positive. So I'm going to get 3b to the 4. What b cubed term have I got? Minus 8b cubed minus 48b squared. And then I'm going to get a plus 80. And all of that is going to equal 0. Okay, now let's look at what the answer is. So the answer, you can see, is kind of a factorized version of this. They're both kind of power of 4 polynomials, because if I have a b plus 2 squared and then I times it by that 3b squared, that's going to get b to the 4. So that's perfect. And I've got the you know, power of degree 4 polynomial here. So now it's just a question of kind of matching them up. I'm going to kind of do some little exam technique here. So essentially, if I didn't have that final answer, what I would probably do is I'd start looking for factors of this, right? I would use the factor theorem. I'd maybe sub in b equals 1, b equals 2, b equals minus 2. And then if you get that equaling 0, you know that that is a factor of it, the b plus 2 or b minus 2 or whatever. You could then do long division to get what's left and then see if you can factorize any further. Bit long, right? Because we're given the answer here, we could be a bit cheeky. If I, for example, label this equation 1, I could actually take the other equation and kind of go backwards a bit and see if they can meet in the middle. So if I could now say, okay, let's consider the equation that they have in the answer. If I just multiply this out and show that it's equal to that, I've shown that they're the same thing, right? So if I was to do the following, let's just get this out quickly. Equals 0. Why don't I just multiply this out? So I'm going to first of all multiply out this little bracket here. So that's going to be b squared plus 4b 4, and then times by this. So it's going to get a bit messy, but probably a bit less messy than other methods, right? So I'm just going to do b squared times by all of this, then 4b times all of that, then 4 times all of that. So I mean, let's just get cracking. So b squared times 3b squared is going to be 3b to the 4 minus 20b cubed plus 20b squared 4b. So that is going to be plus 12b cubed minus 80b squared. It's mad, innit? But that's what we're doing in A-level maths. Minus 80b squared and then plus 80b. All right, one more. So then this is going to be plus 12b squared minus 80b plus 80. Woo! All of that equals 0, but it should get easier now. So remember, do your b to the 4, your b cubed, your b squared, your numbers, etc. So b to the 4, there's only one of them. So this is 3b to the 4. B cubed, I've got minus 20b cubed here, plus 12b cubed here, and that is going to, so that's going to be minus 8b cubed. B squared, I've got plus 20b squared, plus 32b squared, which is going to be, plus 12b squared, which is going to be plus 32b squared. Minus 80b squared, so that is going to be minus, I've got another one here, plus 12b squared. Have I done something silly? Oh no, I've not, that was a b cubed, so we're good. Yeah, so this is 20b squared plus 12b squared, which is 32b squared, and then minus 80b squared, so that's going to get me minus 48b squared. B terms, I've got plus 80b minus 80b, cancels out, plus 80, which equals 0 now. If I'm lucky, which it looks like I am, whew, okay, so I can say that this, same as equation 1, so b satisfies the equation. Part C, it continues. The roots of the equation 3b squared minus 20b plus 20 equals 0. Okay, so that's the quadratic in that second bracket of the thing that we just derived. Are 1.225 and 5.442. The value of b is therefore 1.225, so that makes sense because we're told that b is between 0 and 4, so 3 decimal places. Explain with the aid of a diagram the significance of the root 5.442. Mate, this question is horrible. Alright, 5.442. Let's look. This is x equals 4. So 5.442 is going to be on this side of it. So it's going to be kind of here, right? Let us ask ourselves this. What is b? Because 5.442 is a solution for b in this, right? So then we ask ourselves, like, what is the equation that we derived to get b? And the thing that we said was that for all these b values, the integral from x equals 0 to b is going to be the same as that area of R1. So, for example, for this 5.442b value, it would be this area here. I don't know, why don't we call this R3? And then it would be all of this area here, because we're doing the integral from 0. Maybe we can call this area B for below the x-axis, right? Very coordinated. So if you think about it, if I was to do that integral, I'd get all of this stuff here, that R3, and then that area B is below, so that would be a negative. Get negative integrals there when they're below the x-axis. And the way we set the equation up was we said that whatever this integral is, we didn't quite say it should be equal to r1, we said it should be equal to minus r1. Do you remember, that's how we set the equation up last time? We said it was equal to minus 20 over 3 because the way we made the equation was that that area was below. So why don't we rearrange this and kind of see what happens? If I take that b onto the other side and the r1 onto that side, look what I get. I get r1 plus r3 equals b. Might not seem very significant. I suppose it's relatively significant, right? R1 and R3, if you look at the diagram, they're the areas above the x-axis. So R1 plus R3 is the total area above the x-axis, and we're told that that is exactly the same as the total area below the x-axis, B. So I reckon that's the significance here. I would say between x equals minus 2 and x equals, what is it, 5.442, the total area above the x-axis and the total area below the x-axis are equal. I feel like I need a breather after that one. Really tough question. If you didn't get that, do not worry. I wouldn't expect many people to get that. That is not easy. If you did get it, well done, you're sick at maths. Question 9 looks a lot smaller than the last one, which is good. Right, it looks like we've got a bit of logs. Log a minus log b equals log of a minus b. Show that a equals b squared over b minus 1. Okay, so the show that has no logs in it, right? So we know that our goal is just going to have to be get rid of the logs. If you ever want to get rid of logs, make sure to get a single log on each side. The left-hand side, as it stands, can't get rid of the logs. But if we get it into a single log, really easy. So we're going to use a log law. Log a minus log b, the log law states that that is the same as log of a over b. Log a over b equals log of a minus b. Then a over b just has to equal a minus b, which is lovely. So we're actually pretty much here now. We just need to rearrange for a, essentially. So how do we want to do this? Why don't we just quickly times up by b to get a equals ab minus b squared. I am going to take that b squared onto the other side, take the a onto that side, so I'm going to get b squared equals ab minus a. I'm going to factorize this a out. So then I'm going to get a equals b squared over b minus 1. Fantastic. Right, on the full restriction on the value of b, explaining the reason for this restriction. Okay, so the current restriction on the value of b, we're told it has to be greater than 0 and less than a. That's just what's given in the question. But now it says the full restriction. So there must be something even kind of that restricts it even more, essentially. And look at what we've just derived. We've derived that a is equal to b squared, so this thing's always positive, divided by b minus 1. Now we know that a must be positive because b is greater than 0 and a is greater than b, so a is definitely greater than 0. Look at the bottom here. This thing, if a has to be positive, this thing on the bottom has to be positive. So we know that b minus 1 must be greater than 0. Therefore b must be greater than 1. So the full restriction on b is actually b is less than a, and it's greater than 1. Cool. Question 10. Looks like we have some proofs on our hands. Okay, so prove that for all n as a natural number, n squared plus 2 is not divisible by 4. Okay, so I feel like there's going to be quite a few ways to prove this. The thing that I want to do is proof by contradiction, and the reason why is because it says n squared plus 2 is not divisible by 4. So it would be very easy to get the contradiction of that statement, wouldn't it? The contradiction of that statement would just be n squared plus 2 is divisible by 4. So why don't we assume that? Why don't we assume that n squared plus 2 is divisible by 4? Because then all we need to do is, do some algebra and then hopefully come up with a contradiction. And algebraically, this is going to work out quite well, isn't it? Because that would just mean that n squared plus 2 is equal to 4, I don't know, a, whatever, some number where a is an integer. So let's now kind of try and get a conclusion on n from this, and then we can work back here. So if I take that 2, I'm going to get n squared equals 4a minus 2. This is nice because I can take a 2 out of it. So what happens when we have a 2 times by something. That means that n squared must be even, right? N squared equals even. Oh, n squared is even. It's probably a bit better. Okay, now if I have a square number that's even, that means that its square root is also going to be even. So in other words, if n squared is even, that must mean that n is even. If you don't believe me, just try it out. If n is even, so this is interesting actually. Let's write n, I don't know, as like 2b, for example. You know, if it's even, where b is also an integer. That would mean that n squared is equal to 2b all squared. Well, that would equal to 4b squared. So what does that tell us? That actually tells us that n squared is a multiple of 4. Now I think we're getting close because divisibility by 4 is what we're after here. Multiple of 4. So that would mean that if n squared is a multiple of 4, n squared plus 2 definitely can't be, right? If I have a multiple of 4 and I add 2 to it, it can't be a multiple of 4. I need to add another 4 to get there. So that means that n squared plus 2 is definitely not divisible by 4. So what happens now? Look at our initial statement. Our initial statement is that n squared plus 2 is divisible by 4, but we've just shown that it's not divisible by 4. Now all of this logic in the middle is pretty sound, right? So that means that the only thing that must be wrong here, that could be wrong here, is this top. So n squared plus 2 is not divisible by 4, so therefore that's a contradiction. And that is basically it. We can show some lie that stems from our initial assumption. Our initial assumption must be wrong. Sweet, okay. Part 2. Given x as a real number, the value of the modulus of 3x minus 28 is greater than or equal to the value of x minus 9. Say if this is always true, sometimes true, or never true. Ah, careful. So I almost fell for a little trap. If that was 3x minus 27 in that modulus, then I'd be able to take a 3 out, and then I'd actually have that kind of x minus 9 in the middle, and I'm sure that that would have helped, but it's not. So 3x minus 28, so be super careful there. What I want to do is I want to draw a graph here, actually, and the reason is because it's always nice to draw graphs when we have modulus. It's just easy to see what's going on, right? So if I was to draw the graph of y equals this modulus, and then the graph of y equals the x minus 9, I can then compare. If one of them's above the other, it's always greater than, and vice versa, right? So let's draw the x minus 9. It's going to hit the y-axis at minus 9, isn't it? And it's going to have a gradient of 1, so I don't know. Let's imagine that looks like that. And this is going to be 9 as well. Now, 3x minus 28, forget about the modulus for a sec. It's going to be a straight line. It's going to have a gradient of 3, so it's going to be steeper than that other graph. I'm going to hit the x-axis when y equals 0, which is going to be 28 over 3 if you were to set 3x minus 28 equal. Now, 3 times 9 is 27, so 28 over 3 is just a bit bigger than 9, isn't it? I don't know, let's say it's here, 28 over 3. And we know that it's going to be steeper. So if I was to draw it without the modulus, it would kind of go straight down here. Now the positive bit, nothing's going to change, but then the negative bit's just going to get flipped up, isn't it? It's kind of forming a V shape almost. So this is pretty sweet. We can see that sometimes the V is on top and some other times the line is on top. So if I was to, for example, label this intersection x1 and this x2, I don't really care what the intersections are, but I know that if x is between x1 and x2, then the line's greater. So then the x minus 9 is greater than this modulus graph. Otherwise, the modulus is going to be greater than or equal to it, isn't it? Because if my x isn't in this little bit, the modulus is greater here, and the modulus is greater here. So that would mean that this statement is sometimes true. Cool. Question 11. A competitor is running a 20-kilometer race. He runs each of the first 4 kilometers at a steady pace of 6 minutes per kilometer. After the first 4, she begins to slow down. In order to estimate her finishing time, the time that she will take to complete... Oh, there's a lot of question here, isn't there? Each subsequent kilometer is multiplied 5% greater than the time... Okay, cool. Show that the time to run the first 6 kilometers is estimated to be that. Let's just write them out, right? First kilometer, 6 minutes. Second, 6 minutes. Third, 6 minutes. Fourth, 6 minutes. And then she's slowing down, isn't it? So fifth, it's going to be 6. and then 5% greater than her last one. So her last one was 6. How do I add 5% to it? Times it by 1.05. And then her fifth one, 5% greater than that. So I need to times this by another 1.05. So that's just going to be the same as 1.05 squared. Stick in your calculator, right? So those first 4 6s are going to get me 24. Add 6 times 1.05. Add 6 times 1.05 squared. Now that is going to get me 36.915. Be careful, this isn't your final answer, is it? Because this 0.915 is 0.915 of a minute, but I need to convert that into seconds. So I'm going to get 36 minutes, and then if I do 0.915 times by 60, that tells me how many seconds that is on top. So that gets me 54.9. So if I round that up, that's just going to be 36 minutes, 55 seconds. Cool. Part B. Show that her estimated time in minutes to run the ½ kilometre, so we're generalising, pretty normal, for between r is 5 and 20 is 6 times 1.05 to the r minus 4. That's kind of what we did here, isn't it? We worked out the 5th and the 6th. So like writing this out, the 5th kilometre, it's 6 times 1.05. The 6th kilometre, it's 6 times 1.05 squared. So look what's happening here. This is 1.05 to the 1. The power of the 1.05 is always 4 less than the kind of number of the kilometre. So for the ½ kilometre, it's just going to be 6 times by 1.05 to whatever r is, take away 4. So I reckon that's enough for a mark there, right? Cool. Estimate the total time in minutes and seconds that she will take to complete the race. Okay, how many kilometers are there in the race? There's 20. So the first 4 kilometers, remember 6, 6, 6, 6, so that's the 24. Then I'm going to add the sum of everything else. So let's do a bit of sigma notation here. The sum of, well, all of this stuff here, isn't it, right? So each kilometer, from that 5th one, it takes me this long to complete the race. This is going to start at the 5th kilometer and end at the 20th. So what type of series is this here? It's geometric because I'm timesing by that 1.05 each time. So just to remind ourselves, the sum of a geometric series is a, where a is the first term of that series, times by 1 minus r to the n over 1 minus r. So let's identify a, r, and n for our geometric series, straight to the calculator. So this is going to equal 24 plus, and then this thing. So what's a? A is the first term, which I'm going to get from putting r equals 5 in. So that's going to be that 6 times by 1.05, just the first time where I slow down. Times by 1 minus r. R is the common ratio, so what we're timesing by each time, and that's 1.05. To the power of n, super careful. You're probably used to this thing here being n. However, that would only be the case if r equals 1 was here, because then you would have these 20 terms. But we start at 5, so we're actually losing the 1, 2, 3, 4 term, so we've actually only got 16 terms. This is going to be a 16. They can catch you out on that. Times by 1 minus the r, which is 1. Right, what have we got? Let's put this straight into the calculator. 24 plus big fraction, 6 times 1.05 times by 1 minus 1.05 to the power of 16, close bracket, over 1 minus 1.05 gives me 173.04219, blah, 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 blah. Last thing we need to do, just convert this into seconds. So these are the 173 minutes. And then to get the last bit in seconds, I would do that 0.04219 times by 60. That gets me 2.53, blah, 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 blah. Rounding that up to the nearest second is going to be and 3 seconds. Cool. Question 12. F of x equals, what is that? 10e to the minus 0.25x times sine x. Okay. Show that the x coordinates of the turning points of the curve of the equation y equals f of x satisfy the equation tan equals. Okay, so turning points, what we're doing, we're differentiating and we're setting equal to 0. This function here is the product of two functions, so we're going to need to use the product rule. So we're going to be writing down the first, differentiating the second, plus differentiating the first, writing down the second. So the derivative of f of x is equal to, I'm going to write 10 e to the minus 0.25x and then differentiate that sine. Sine differentiates to plus, now I'm differentiating that e bit. So it's going to be 10. When you're differentiating e's, all you need to do is differentiate this bit in the power. So that's going to be minus 0.25, and then just write down the e again. So times by that, and then I need to write down that sine x. Right, let's simplify a bit. Can't really do much to that first term, so I'm just going to write that out again. Second term, the only thing I can really do is just times these, so that's going to be minus 2.5. So what I want to do is I want to set this thing equal to 0 to find the turning point. So solving that equals 0, I can clean it up and I can actually divide through by these e's. Now you might be thinking, wait a minute, didn't you have some big rant a few questions ago about dividing through by variables? And I did. But the only thing we need to worry about there is if that variable can be equal to 0. Think about an exponential. Think about the graph of y equals e to the x. It goes so close to 0, but it never quite hits it, does it? So I know that I can divide by these exponentials willy-nilly because I know that they're never going to be equal to 0, so I'm not losing any solutions or anything. So I'm going to do that, and then I'm going to also just bring this 2.5 sine x over to the left-hand side. I'm going to get 2.5 sine x, these are gone now, is equal to 10 cos x. Right, super simple now. Divide by that 2.5, divide by the cos. So I'm going to get sine over cos, which is 10x, equal 10 over 2.5, which is 4. Cool. That'd be sketch. Okay, so figure 3 shows a sketch of the part of the curve with equation y equals, okay, f of x, which is what we had above. Sketch a graph of h against t, where h of t, okay, it basically just equals the modulus of what we have above. Okay, so this is actually going to be quite easy because they give us what the other one looks like. So to draw the modulus of something, when we already have the initial graph, is super easy because anything that's below the x-axis just gets flipped. So everything that's above, nothing happens to it. So this thing here, exactly the same. This bit down here that's on the bottom, flip it up. I'm going to butcher this, but I don't care because we're not doing arts, right? So then I've got another loop here. So you can see what's happening. They're just going down a bit. You know, they're a bit more wavy than I'm doing them, but again, doesn't matter. So let's do a couple more of these. You can see it just going down and down. That e term, as t gets bigger, is just making the peak of these smaller and smaller each time. This is going to be h of t. I'm happy with that, to be honest. I'm happy for that. Showing the long-term behavior. The long-term behavior is, look, going down in it. Really, really small. Just like a negative exponential is going to go close to 0. This is too. Okay, the function h of t is used to model the height in meters of a ball above the ground t seconds after it's been. Using this model, find the maximum height of the ball between the first and second bounce. Okay, that's cool, that's cool. So think about it. I drop it, it goes here, or I chuck it in the air, whatever. I chuck it in the air, it goes up here, and then first bounce is here, and then the maximum height between the first and second, so what I'm looking for is this thing here, aren't I? Okay, maximum, what we're thinking stationary points, turning points, right? Oh look, what do we do in part A? We're told exactly the equation that we use to find these turning points. Super easy. Quick word of warning. Whenever we're using trig within calculus, please make sure that you put your calculator in radians. Super important, because they're going to be cheeky. They don't tell you that all of the time, but please make sure you do it. So I'm going to get my calculator into radians now, and then I'm just going to go, right, inverse tan of 4. Inverse tan of 4 gets me 1.3258 ... But I need to be careful, don't I? Because remember, I'm looking for this. This is the second peak. My calculator is going to give me the first value of tan that satisfies this. However, if you think of that tan graph, you have loads of solutions and you jump by 180 degrees or pi radians for each solution. You've got the first solution, which is this, but I want the second one, and that is going to be pi later on. So the one that I actually want, I'm going to add pi to this, and that's going to get me to a couple of decimal places, 4.47, and that's going to be a t value here. So this is tan x equals 4. We changed to t in this one, so let's just be really proper and call it tan. What do we now need to do? Well, we need to find that maximum height. We've got the time value, so we just sub it straight into that equation, right? So all we need to do is we now need to say h equals the modulus of 10e to the minus 0.25 times 4.47 times by sine 4.47 straight to the calculator here. 10 e to the minus 0.25 times 4.47 times by sine 4.47. So this gets me a negative number, which is minus 3.17. But remember, I put it in a modulus, so I just take the positive version of that. So I'm going to get 3.18 to 2 decimal places. And that is, I believe, in meters. So 3.18 meters is going to be the height after that first. Explain why this model should not be used to predict the time of each bounce. Well, let's have a look at the model. It looks like this. So you imagine, right? You chuck your bouncing ball in the air, goes up all the way up, and it goes dun, bounces, and then it goes dun, 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 and then, you know, as it's going to the floor, it's about, you know, it's only going up this much, and it's bouncing really, really frequently, isn't it? Well, let's have a look at this. This model looks to nicely predict, you know, the changes in height. Obviously, I chuck it, and then it goes down and down. However, look at the jumps in time. They're all the same. Does it make sense that when I chuck it in the air and it goes 50 meters in the air, and then when it goes about 4 centimeters, the time it takes to do that is exactly the same? No, it doesn't, does it? So that would be why this model's probably not perfect for this situation. What you would have to do, you would actually have to amend the term inside the sine. So you would have to do something to that to kind of have it then, you know, go smaller on that t-axis as well as the vertical axis there. So I would just say something along the lines of, just make the examiners happy, model predicts time between bounces will always be the same. I don't know, you can keep going if you want, more words, more chance of getting the mark right, when in reality, they would decrease. Something like that. I'm sure that is more than enough. 13, we are getting through this. Can't be long now. The curve C with equation y equals all of that stuff, where p and q are constants, passes through the point 3.5, okay? And has two vertical asymptotes with equations x equals 2 and x equals minus 3. Explain why you can deduce that q equals 4. Okay, so it's about these asymptotes. Vertical asymptotes happen when we have 0 on the bottom of a fraction. And that's because you can't actually have 0 because you'd be dividing by 0 and it goes up to infinity. And that's what happens with asymptotes. As you get closer and closer to it being 0, they go really, really close up to this line, and that's what an asymptote is. And then it never quite hits it, and then it kind of jumps over it. So we're told that one of them is at x equals minus 3, and that makes sense because we have an x plus 3 on the bottom. If you put an x minus 3, it becomes 0. So the other asymptote is just going to be got from putting the other bracket equal to 0. So 2x minus q equal to 0. And we're told that that happens at x equals 2. So in other words, 2 times 2 minus q must equal 0. Therefore, 4 minus q must equal 0. Therefore, q must equal 4. So it's all in the asymptotes, right? Show that p equals 15. So not much to do with asymptotes here, but we are given another piece of information. It passes through the point 3.5. So just sub it in, right? So a half is going to be y. And we're going to get p minus 3x equals, we now know that q equals 4, so we get, I wrote 3x, but we can actually sub in x equals 3 there, can't we? So let's put 3 times 3, and then we get 3 times 2, that's the 2x, minus the 4, and then we get the 3 plus 3. So what do we do now? Let's just work it all out. So we get p minus 9 over 3 times 2 is 6, take away 4 is 2, times by 3 add 3 is 6. So 2 times 6, that should be a 9. 2 times 6 is 12. I'm going to times that 12 up, so I'm going to get 6 equals p minus 9. So p must equal 9 add 6, which is 50. Cool. Figure 4. Okay, this one looks big. We got an 8 marker, so just like, get comfy, right? Here we go. Figure 4 shows a sketch of the part of the curve C. Okay, the region R is bounded by the curve C, the x-axis, and the line of the equation now. Show that the exact value of the area R is all of this. Don't worry about all of the luns and stuff yet, because, you know, we're 8 marks away from that. So instead, just ask yourself, find the area R. How are we going to do that? It's clearly an integral, right? It's an integral. It's going to be the integral of the curve, and we have the curve. It is 15 minus 3x over 2x minus 4 times by x plus 3. So then, all that remains is getting the limits. First limit is 3, we're told that. The second limit is where this thing hits the x-axis. Where does it hit the x-axis? It's when y equals 0. So how are we going to get this equation to be equal to 0? If it's a fraction, all you need to do is check if the top is. So essentially, you're solving p minus 3x or 15 minus 3x equals 0, which gives you x equals 5. So that is going to tell you the top limit here. So now we've just got an integral. I say just, it's a big integral, right? How are we going to integrate this? Unfortunately, you're going to have to do partial fractions. So what we're going to do is we're going to split this thing up into partial fractions. So we're going to say that this is equal to a over the first factor on the bottom. So a over 2x minus 4 plus b over the second, x plus 3. Okay, so what you want to do with partial fractions is you want to times basically by all of these denominators. So I'm going to times by 2x minus 4 and x plus 3. So that's going to leave me with just the top on the left-hand side. And then a times by the 2x minus 4 cancels, and I get the x plus 3. And then the other way around. So the good thing about this is supposed to be true for kind of any x. So we can just put x values into this equation that are nice. So the first one, I'm going to put x equals 2. Why am I going to do that? It's going to make this thing just go away, just leave me with an equation with a. So x equals 2 is going to get me 15 minus 3 times 2 equals a times 2 plus 3. And then this is just going to be plus b. I'm going to write it out, but it goes to 0. So that's gone. Okay, so what do we get? 15 minus 6, which is 9, equals a times 5, so 5a. So a is going to equal 9 over 5. Right, similar thing for the other. We are just going to sub in a value of x that gets rid of this thing here, get the value of b. So that's going to be x equals minus 3. Okay, 15 minus 3 times minus 3 is going to equal a, minus 3 plus 3. We know that's a goner. Plus b times 3 times minus 3 minus 4. So minus 3 times minus 3 is plus 9. 15 add 9 is 20. Equals, a term goes, 2 times minus 3 is minus 6. Take away another 4 and I get minus 10. So I get minus 10. So b is going to equal minus 24 over 10. About maybe halfway through the question now. Not even, I'm not sure. Let's see. Okay, so we've not even integrated yet. Now, we now know our integral is this, 5 over 3 times by a, which we know is 9 over 5. And then it's a over this 2x minus 4. And then plus b, but we know b is negative, so I'm going to bring that negative out here. And then 24 over 10 times by the x plus 3. Okay, now, this is probably going to get messy. I just want to make sure we do everything we can initially, just reduce the kind of level of messiness as much as we can. So the first thing I'm noting, right, I've got this 10 down here. I've not got one here, but I could do. Because I can take a 2 out of this bracket here to mean that this thing turns into a 10. So I'm going to get 9, and then I'm taking the 2 out, timesing it by that 5 to get 10. So I'll then get an x minus 2 here. This stays still, so 24 over 10 at x plus 3. Why have I done that? Because constants, I can take them outside of the integral. It's going to be super useful here, just because it's going to get messy, right? So if I bring a 10th outside here, just leaves me a few less things to worry about. So I've got 9 over x minus 2 minus 24 over x plus 3. I think at this point we can integrate. So this is where the lunds are going to come. So this is going to equal a 10th times by 9 ln of x minus 2. So you just integrate x minus 2 the same as you would x, because the derivative of x minus 2 is the same as the derivative of x. So there's no kind of real like inverse chain rule or substitutions that we need to do here. Minus 24 ln of x plus 3. Okay, let's sub some numbers in. We're going to get quite a lot of brackets and stuff going on here. So what I'm going to do is I'm going to do 10th, and then I'm just going to do a big bracket, sub all these numbers in, making sure I get the signs right. So I'm going to sub in 5 to this thing here. So it's going to be 9 ln of 5 take away 2, which is 3. Minus 24 ln of 5 add 3, which is 8. And then minus the 3 terms. So it's going to be minus 9 ln of 3 take away 2, which is 1. That's nice, because ln of 1 is 0, so one less thing to worry about. And then it's going to be plus 24, because if you think about it, I'm taking away this whole thing, so I'm taking away a negative, so it becomes a plus. So plus 24 ln of 3 plus 3, which is 6. Woo! Right, so look at the answer. We want ln 2s and ln 3s. So I can see I've got a ln 3 here, but then these other lns, I can be a bit cheeky and turn them into 2s and 3s. So let's keep the 10th out here. 9 ln 3, keep you here for now. Minus 24. I can use a nice little law here. 8 is 2 to the 3. So if I rewrite this as ln of 2 to the 3, I can then use the power law, bring that 3 to the front, and I'll have a ln 2. 9 ln 1, ciao. Ln 6. What we're going to do here. I need to get 2s and 3s. 6 is 2 times 3. So using the addition log law, I get this is ln 2 plus ln. I think we're getting there. I really hope this is right. So a 10th. Scroll down again, because there's been a lot of maths here. Okay, 1/10. 9 ln 3, let's keep you here. I'm going to bring this 3 here, so I get 3 times 24, which is 72. So 72 ln 2 plus 24 ln 2. Plus 24 ln 3, which equals 1/10 times by. So ln 3 is I've got 9 ln 3 plus 24 ln 3, which is going to be 33 ln 3. Minus 72 ln 2 plus 24 ln 2 is going to be minus 48 ln 2. Oh, I think we're getting there. Now I can bring that 10th back in. So I'm going to get 33 over 10 ln 3 minus 48 over 10, which is going to be 24 over 5 ln 2. Is that the right? So I'll get a ln 2 plus b ln 3, where a and b are rational, and both of these are rational. Whew! Question 14. Last question. Here we go. The curve C in the standard Cartesian plane is defined by the equation x equals 4 sine of 2y. Cool. Find the value of dy by dx at the origin. Okay, careful. We are not given y in terms of x. We're given x in terms of y. So we can't just go, dy by dx equals. But luckily it's not too bad, because we just do dx by dy equals, and then once we have that, we just do 1 over it. It turns out derivatives kind of behave like fractions, which is just good news, isn't it? So how we're going to differentiate 4 sine of 2y. 2 is going to come out to the front, giving me 8, and then the sine is going to go to cos. So simply, dy by dx is just going to be 1 over this. Not too bad at all. At the origin, y is equal to 0. So at the origin, dy by dx just going to equal 1 over 8 cos 0. Cos of 0 is 1, so that's an 8. Cool. Use the small angle approximation. So we've got another one of that, so they like it. They like it. I think we've had 2 now. Sine of 2y. Okay, so the small angle approximation for sine essentially says that when theta is small, sine theta is just about theta. So find an equation linking x and y. That means that x is basically approximately just going to equal to 4 times 2y. Which is going to get me y is approximately equal to, well, we'd have 8y is approximately equal to x, so y is just about 8x near the origin. Explain the relationship between the answers to A and B. Okay, so near the origin, y is approximately equal to an 8x. This is just a straight line, isn't it? Y equals mx plus c, right? And in this case, m is just going to equal to an 8th. The gradient of this line is going to equal about an 8th. But look, that is the gradient we derived in part A. Remember, dy by dx represent gradients, and it says at the origin, the gradient is an 8. So that works. They back each other up, don't they? So equals the gradient derived in part A, and I reckon that's enough. Cool. Show that for all points xy lying on C. Okay, I like this. I like this. I think it's very, very important to know how to represent things, especially using trig identities, you know, if you've got it in terms of y, but you want it in terms of x, etc. Because if you think about it, we've already got dy by dx. So you might say, what? Why are we finding dy by dx again, right? Because we know that dy by dx is 1/8 cos of 2y. That's in terms of y. We want it in terms of x. What we're going to do? X is equal to 4 sine of 2y. So here's the thing, right? If this cos of 2y was a sine of 2y, we'd be sorted. We'd just say, boom, that's x, or 4x, or 2x, or whatever, and we're good. But we have a cos, we want a sine. What do we do? Now, please remember this, because it happens loads, it happens with parametric equations, etc., etc. You're just going to use cos squared plus sine squared equals 1. It's very easy to change a cos into a sine into a cos, using this identity. So this tells me that cos of 2y is equal to the square root of 1 minus sine squared of 2y. Now this is good, isn't it? Because look at this. Sine of 2y is just equal to x over 4, isn't it? So straight away, I know that this derivative dy by dx right here is going to be equal to the following. 1 divided by 8. Instead of cos 2y, I've just got 1 minus. Now sine squared of 2y, sine of 2y is x over 4. So it's just x over 4 squared. So we're pretty sweet now. Let's just look at what the answer wants. We want, okay, so look at that square root at the bottom. We want just x squared. We currently have x squared over 16, don't we? But we want an x. So we kind of need to like times something inside that square root to bring those numbers up, don't we? We can do that. You see, we've got this 8 on the outside. Essentially, I want to times this thing in the square root by 16, don't I? Now, 4 squared is 16. So if I bring a 4 from outside the square root into the square root, it's going to turn into a 16. So 8 is 4 times 2. I'm going to split that up into 4 times 2, leaving me with just a 2 here. The 4 is going to go inside the square root and turn into a 16. And then it's going to times what I have inside. Whew. So what's going to happen? I'm going to get 1 over 2 times the square root of 16 minus x squared. Whew. And we're done. That was not an easy exam. Some very tough questions in there. It would be interesting to know what everyone thought of that. Now listen, me and a load of people much smarter than me have made a website with the sole purpose of sorting your life out when it comes to A-level maths. Got video tutorials covering the whole syllabus. You'll have 1,000,001 questions to practice, proper exam style questions. You'll be able to generate exams and much more. It's completely free to start and set up an account. There is a paid version, but start on the free one, see what you think about it. That's aitutor.co.uk. I am gonna go to bed.